let's get started with our 11 a.m. discussion. So today we're mainly going to be talking about sampling and aliasing. And I think this is definitely one of the more challenging topics in the course. So definitely if you have any questions, like always feel free to reach out, ask on Piazza and whatnot. And we're going to do a brief recap of what's been going on because there's been a lot going on. So we're kind of at our final module of the course, which is on digital signal processing. And what we're going to do is we're going to kind of learn how signal processing works from end to end, from continuous to discrete back to continuous. So one way to think about this is we have some continuous time signal, x of t. We're going to sample it using a computer, most likely. So we're going to get a bunch of samples that are discrete. And given all of these discrete samples, we're going to have some, so we have x of t, and we're going to have some discrete signal now, x of n. I use these square brackets and n to distinguish it. We're going to put it through some digital filter. And a digital filter is very similar to something you saw in the circuits module, like all those low and high pass filters you design, except they're just in discrete time now. We're going to get some sort of output now. Maybe it looks like this, doesn't really matter what it looks like. Y of n. And the last thing we want to do is, let's say this was like some audio signal, like we sampled it, we did some processing on it, and now we want to, our speaker wants to transmit this audio back into the real world. We want to project the audio again back into real audio that we can all hear. So to do that, we got to do interpolation. And interpolation is really just a way to connect the dots. So it's probably going to look something like this. So reason we do all this in this really complicated way, from going from continuous to discrete, do something in discrete and going back to continuous, is because our computers all behave in discrete time. And on Monday, we took a look at how to do interpolation, which was to take a bunch of discrete samples and construct something continuous out of it. In other words, we took discrete samples and create a continuous function, y of t out of it. And today, we're going to look at the exact opposite process, which is sampling, where we have some continuous signal, we sample it at some evenly spaced intervals to create a discrete signal out of a continuous one. So any questions about what's been going on so far? Give you a moment to take this all in as well. All right, moving on. So now that we've seen how to do interpolation, you might remember that it was possible to do interpolation using all these basis functions. You can use a linear basis in order to do piecewise linear interpolation, which is just connecting a straight line between all the samples. Another way was to do polynomial interpolation, where we construct a degree n polynomial out of all of our samples. And another way to do it was just through sinc interpolation, where sinc was this, Professor Archok likes to call this the octopus function, where sinc of t is just sine of pi t all over pi t. And polynomial interpolation, you can kind of think of the basis as 1 t, and then t squared, and so on and so forth. All right. So the way to do all this reconstruction was just to take a linear combination of all of our basis functions. And I don't think there's anything too special about this. It's just that different basis functions give you different shaped reconstructions, where this linear interpolation gets you this very sharp like lines between each samples. Sinc and Lagrange or polynomial get you this really smooth like reconstruction between samples. And there are a bunch of other types of reconstructions that you can do. And for today, we're mainly going to be focusing on sinc interpolation, because it turns out that Lagrange interpolation is very like susceptible to something called overfitting, where like you can fit a degree n polynomial to these data points or to these like sampled points. But if you look at any points that haven't been sampled, like sinc interpolation is very unstable at the endpoints, because polynomials by nature just grow without bound if you go to infinity. So any questions about interpolation and basis functions? All right. So main topic for today, as we've kind of said earlier, is going to be on sampling, and mainly on this unfortunate phenomenon that occurs called aliasing. So we can take a continuous time signal and we can always sample it by just evaluating it at every t seconds. And we always like to evaluate our signal, our continuous time signal, at evenly spaced intervals. So we evaluate at t, then at 2t, 3t, just evaluate it at every multiple of t. So we're just taking these snapshots. So red is going to be our sampled, and blue is going to be our original continuous signal. And just some vocabulary to take into account. T, sometimes like capital T, sometimes capital TS, is our sampling period. In other words, our space between samples. And omega S, which is 2 pi over T, is just our sampling frequency. And this is just because omega is always equal to 2 pi over T. In other words, because we're sampling periodically, there's a frequency behind the way we're sampling. So any questions about how sampling and aliasing, I guess, or sampling works so far? I haven't really talked about aliasing yet. We're mostly on the vocabulary. Okay, moving on. It turns out that there is this very important theorem called the Shannon-Nyquist sampling theorem, which says that if we have some continuous time signal, x of t, with some maximum frequency, omega max, it's always possible to reconstruct the original signal using sinc interpolation if we sample fast enough. And how fast is fast enough? Well, fast enough is at frequency greater than 2 times the original maximum frequency. So kind of to paint an intuitive picture of what's going on here, like we can think of a bunch of these like continuous time signals as sinusoids. For example, if we have sine of 4 pi t, then we know that omega is equal to 4 pi. Just the way sinusoids work. If we have another sinusoid, which is perhaps cosine of 6 pi t plus sine of like 4 pi t, then it has two frequencies, one at 6 pi and one at 4 pi. So here, omega max is just the greater of the two. It's just the maximum frequency of the continuous time signal, which is the sum of sinusoids. And any arbitrary continuous time signal can be broken down into a bunch of sum of these sinusoids through something called Fourier series or through the Fourier transform. We're not going to talk too much about that today, but just know that it exists, and really that continuous time signals can have a maximum frequency. And we're mainly just going to be talking about a bunch of sinusoids. So sinusoids always have a defined frequency, and here the maximum frequency, because we just have 6 pi and 4 pi, is just 6 pi. Okay, and let's see. Other things to note. Because omega s is equal to 2 pi over ts, and we need this to be greater than 2 omega max to have a perfect reconstruction. This tells us that ts has to be strictly less than pi over omega max to guarantee a perfect reconstruction. So might be a little unintuitive at first. It definitely was for me the first time I saw this, because the smaller your sampling rate is, the more samples you're taking. In other words, here we're taking like samples, I think it's like 2.5 or something. I don't know the exact rate here. I think these are all typos here, but in other words, if t is equal to 2.5, we're taking a snapshot every 2.5 seconds. Whereas if we take a snapshot every 1 second, we're taking a snapshot more often. So because this t is smaller, our space between samples is smaller, so we have more samples. So here we have much more samples than on the right than on the left, because our sampling rate is smaller, our sampling period is smaller. And more samples always is a better thing because we have more information. So if we sample fast enough, we'll get enough information to perfectly reconstruct a sinusoid using sinc interpolation. It's kind of the amazing thing where you can take any continuous time signal and always reconstruct it using sinc interpolation if we sample fast enough. All right, any questions about the sampling theorem? All right, moving on. Main topic we want to take a look at today is aliasing, which is kind of what happens when sampling goes wrong. So another way to say what aliasing is, what happens when we don't sample fast enough. And this is mainly due to the nature of sinc interpolation, where sinc interpolation is very naive, meaning it'll always try to pick the easiest thing possible. Similar to how Lagrange interpolation picks the lowest order polynomial that can fit all the data points, sinc interpolation will always pick the lowest frequency sinusoid that fits all the data. And just to give an example here, and we'll see much more of this once we get to the worksheet, we're gonna get to it really soon. If we have the same sinusoid, like the one we just talked about above, and sample it with sampling rate t equals 6, in other words, we take samples every 6 seconds apart, then it turns out that sinc interpolation is going to take a look at these two samples and reconstruct some lower frequency sinusoid out of all of this. So our blue signal is our original signal, whereas our perhaps orange signal is the reconstructed. So notice how our reconstructed signal from sync interpolation isn't our original signal when we want to always reconstruct our original signal. And this is because we haven't sampled fast enough. If we had taken more samples, then sync interpolation would see these samples and say, hey, I need to go up and I need to go back down. But here, it just sees these two samples and says, well, I can just go down and so forth. So it's kind of what's going on here. Any questions about how this all works? All right, so let's take a look at the discussion worksheet now. And first question is really just building a lot more intuition on how sampling works as a whole. So give everyone some time to work on this. Just going to take a look at the first couple of parts where we have a sinusoid, sketch it, sample it at a bunch of sampling rates, and we try to reconstruct something out of it. All right, let's start taking a look at how to work through this question. So first part, we're just given cosine of 2 pi of t. We're just sketching it for t in between 0 through 4. Nothing too challenging here. Just gonna mark my points here. Perhaps I should give myself a little more room. And since the frequency of this sinusoid is 2 pi, we know the period is equal to 1. So we complete one full period every second. So we can sketch it kind of like the following. Next, we want to take a look at some discrete samples of the signal, sampled at various rates. So this is really just a drawing exercise, and it'd be good to just copy this over instead of retrying it every time. So we're going to start with a sampling rate of 1/4, and all we're doing is just evaluating this signal at every 1/4 of a second. So it's going to look something like this. Hold on a sec. Doesn't. Sorry, this is a little too close apart. There we go. And so forth. And just notice how we're taking 4 samples every second because t equals 1/4. And from here, how would we reconstruct this if we only had these discrete samples? Like, how would sync interpolation do this? It's all still very high level. Because we see all these samples very close to each other, we have to go down and then back up. We're just going to pick the best sinusoid that can do so. And it's going to be a perfect reconstruction because all these samples are very close apart, and we can see this up and down like movement. Now let's take a look at t equals 1/2. Perhaps let's just copy this over again. Maybe one more just for another example. But now we just take samples every 1/2 second. Actually, 1/2 second would be down here, and then here, and so forth. So we take 2 samples every second, and sync interpolation will then, because we have to go down from here, we go down, then back up, and so forth. So far, our reconstructions have been pretty good, and that's because our samples are very close to each other. And last thing to do is to take a look at t equals 1. And what happens when t equals 1? Well, it turns out that if you sample at 0, then at 1, then at 2, then at 3, and then 4, we're sampling all 1s. And now that we've sampled all 1s, you might see where the aliasing starts coming in, because if our discrete samples are all 1, like if we were just given all these 1 samples, like the easiest thing we can fit to all these 1s is just the function 1. So this is where the aliasing starts kicking in. So any questions about what we've done so far? And you might ask, like, the sampling frequency here is 2 pi. And the Shannon-Nyquist theorem tells us that t needs to be strictly less than 1/2 for a perfect reconstruction. But at t equals 1/2, we got a perfect one. And why is that the case? Well, in other words, the Shannon-Nyquist theorem says that when t is less than pi over omega max, we are guaranteed a perfect reconstruction. But it can also mean that for some greater t, we may have a perfect reconstruction. Like, it's a bit iffy on the wording, but in other words, when we said, like, where was it again? It was over here where we said we can always reconstruct. This is guaranteeing a reconstruction. But there are possible t's, like this example here, where we may have a perfect reconstruction, even though we haven't satisfied this sampling rate, this ideal sampling rate. And we're actually going to see an example in the next part where we sample at 1/2 again for a sinusoid with frequency 2 pi, where we don't get a perfect reconstruction. All right, so just to answer some quick preliminary questions, I've already kind of given the answers to these. What is the maximum frequency here? Since our sinusoid is just cosine of 2 pi t, omega max is just 2 pi. And in hertz, in other words, it's 2 pi radians per second, or in hertz, it's going to be 1 hertz. And this is just because f is equal to omega over 2 pi. All right. I'll give you some time to think about the next parts, and hopefully once you start repeating for this sine wave now, you'll notice the effects of aliasing again. I can scroll back up to part C, yeah. All right, let's take a look at part D now. If I sample every capital T seconds, what is the sampling frequency? This is just a definition where omega is equal to 2 pi over t. In other words, omega sampling is equal to t, 2 pi over t sampling. But here, the sampling rate Ts is equal to t, so omega s is equal to 2 pi over capital T. Next question asks, what is the smallest sampling period t that would result in an imperfect reconstruction? So this refers back to the sampling theorem. The sampling theorem, the Shannon-Nyquist sampling theorem, says omega s has to be greater than 2 omega max. And here, since omega max is 2 pi, this means this needs to be greater than or equal to 4 pi. And since we know the sampling period, t, is equal to 2 pi over omega s, we can say that 2 pi over omega s is greater than 4 pi. Sorry, 2 pi over t. And this tells us that t needs to be less than 1/2 for a perfect reconstruction. So if t is greater than or equal to 1/2, we may have an imperfect reconstruction. And then it asks, what is the smallest sampling period t that results in an imperfect reconstruction? And if this is possible when t is greater than or equal to 1/2, then the smallest such t is t equal to 1/2. So, any questions about what's going on so far? Do we need to check for the case of equal for e? And it might be just the way this question is worded. Maybe we should, instead of would, say may. But we don't need to necessarily check this. Like, it's always good to check, but it also depends on the sinusoid you're given. So all this is saying is if t is equal to 1/2, we may have an imperfect reconstruction. And now if we repeat the process of sketching sine of 2 pi of t, hopefully we're able to see this now, where I'm going to first sketch what sine of 2 pi of t looks like. Jeez, my drawing is just... All right. So we have sine of 2 pi of t, and let's go back and suppose our sampling rate is 1/4 now. So if we sample 4 times a second, we're going to get something that looks like this. And sync interpolation again, because we see all these up and downs, are going to follow it. And we're going to get a perfect reconstruction. Now, if t equals 1/2, this is the case we've kind of been talking about and saying we may have an imperfect reconstruction. And well, here's one case where it can happen. And hopefully you can see this now, where we have 1, 2, and 3. And if we sample every 1/2 second, we're going to see all zeros. So even though our maximum frequency is 2 pi, like sine of 2 pi of t has a maximum frequency of 2 pi, because t is equal to 1/2, we aren't guaranteed a perfect reconstruction. And you can see the reconstruction here. Because we've sampled all zeros, we're just going to take the simplest approach and just interpolate all zeros. And if you pick anything larger, if you pick another like multiple, let's say we pick t equals 1, then again, we're going to see some sort of different signal that recovers all zeros again. If we pick something in between 1/2 and 1, then we're going to see some sort of aliasing, where this is aliasing as well, but we're just going to see something that flows like in between. So I think just one example would be something that looks like this. All right. Any questions about what's gone on so far? I think the main takeaway here is that the Nyquist theorem tells us that we always have to sample at frequency twice the maximum to guarantee a perfect reconstruction. And if we're at exactly twice the maximum frequency, we may not, or we may have a perfect reconstruction. And it all depends on the phase of the sinusoid. So you can kind of think of this sinusoid as having a phase of pi/2 or negative pi/2. And that's like the reason we're seeing this aliasing occur. Whereas here we had, it was cosine of 2 pi of t. This has 0 phase. So we get a perfect reconstruction even though we're at the boundary. All right. Moving on to the last part. So I'm probably going to skip part A. I don't think part A is too important. Like we've kind of already seen what happens. And it's just asking, at what period can we sample at to recover identically 0, to reconstruct an identically 0 function? And again, since this is sine of pi/5t, if we let our sampling rate be some sort of multiple of t, then we're just going to sample all zeros. And hopefully you should be able to see that just through the way the sine function works. Like sine of 0 is 0, sine of pi is 0, so on and so forth. And I think the last part, this is probably the most challenging part of the entire discussion, and took a little extra time in the previous discussion to talk about this, and I'm honestly still a little conflicted on how I should teach this, and I think we'll talk about like the fundamentals first and then talk about more the brute force way to do this. So essentially what's going on here, our original signal is sine of pi/5t. And we sample it somehow. If we sample it, sampling just means evaluating at every multiple of t. So this is the same thing as saying this is equal to sine of pi/5 n times capital T for n equal to 0, 1, 2, so on and so forth. And now we're asking if, like, what period can we sample at in order to recover this aliased signal, x of t is equal to minus sine of pi over 15t. And in order to recover this alias signal, we somehow need our samples to be x of n is equal to, we need this to be equal to sine of pi over 15 times n. So, sorry, pi over 15 times, yes, n. So if we see samples pi over 15n, then our alias signal is going to be pi over 15t. And, or sorry, minus sine of pi over 15t. And we can do this multiple ways. I think one way to do this is to do this graphically, where you just take sine of pi over 5t, sketch it out. Like pi over 5 means we make a period every 10 seconds. And then to sketch sine of pi over 15t, this would be a period every 30 seconds. And kind of just see where they overlap, really. And let's think about this a little more carefully. Sorry, this is all sines instead of cosines. Hold on a sec. Sine goes upward. So we had sine of pi over 5t. And then we want to sketch minus sine of pi over 15t, which will look something like this. Hold on a sec. Let me fix my drawing a little. And so on and so forth. And if we look at the intersection points, then we can see where the aliasing occurs. So that's one way to do this. And the more brute force way to do this, and this is definitely something that this is the most we're ever going to ask. Like I suggest, if you want to fully understand this, just write it on a cheat sheet and so on and so forth. All right, so this is something I'm actually doing post-recording. Took a look back and wasn't too happy with how everything went, and thought it'd be good for me to just recap once more how the whole brute force method works for sync interpolation. And this is after I took a look at more examples, and I think really the best way to understand this is to just open up a Jupyter notebook, plot some data, sample it, and kind of see how the aliasing effect works. So talk a little bit about the theory first, and then we'll look at some examples and finally go back to the discussion problem. So we're going to start by looking at some sinusoid. Let's say given some sinusoid x of t, which is equal to, I'm just going to say for now, cosine of omega naught t plus phi. You might remember that omega naught, this is just the frequency of the sinusoid, and phi is just the phase. And we're going to sample this, sampled at rate capital T. So given the sinusoid, we're just going to take snapshots every t seconds. So this should all be review, but now the way discretization, or the way sampling works, the discrete samples themselves, these are just going to be evaluations at every t. So they're just going to take multiples of nt and evaluate this. So it's going to be cosine of omega naught nt plus phi. And from here is really where the challenge now comes in, where sinc interpolation picks the reconstruction with lowest frequency. I'm going to put this in like bold and lowest frequency. And you got to think about what our options are now when we like mean lower frequency. Like, what does it mean? You got to be like lower than something, right? So we can say the simple option, like the simplest option is just to kind of take a look at our samples, like cosine of omega t, and just interpolate x of t is equal to cosine of omega naught t plus phi. And this is just by like substituting n equal to t over capital T. This is how the like reconstruction works. Because we sampled, this was like a substitution of t is equal to n capital T. We just go backwards, where we just now substitute n is equal to t over capital T to reconstruct the continuous signal. So that's our first option. And the other option, or another option, maybe we can, instead of saying another option, like we can notice that x of n is also equal to cosine of 2 pi n minus omega naught nt minus phi. And this is because cosine of 2 pi n minus x is equal to cosine of x. Like cosine is an even function, so cosine of x equals cosine of minus x, and you can just add any multiple of 2 pi to make it the same. And if we kind of pull out the frequency here, you can notice that, let's just factor out the n. This is going to be 2 pi minus omega naught t times n minus phi. And again, if we reconstruct this, we can reconstruct, or maybe say now another option is in fact x of t is equal to cosine of 2 pi minus omega naught t, times t over capital T minus phi, and then we can just simplify this a little bit, which is then going to be 2 pi over t minus omega naught times t. And really from here, it now kind of boils down to how we picked our t, our original sampling rate. So, like we can say if omega naught is, let's see, so the sampling theorem says, like, maybe if you go back to our slides, our sampling theorem says that we need to pick t less than pi over omega max, right? So if t is greater than or equal to pi over omega max, or in this case, omega max is just omega naught. So if t is greater than or equal to pi over omega naught, this is the same thing as saying omega naught is greater than or equal to pi over capital T. And this shows that 2 omega naught is greater than or equal to 2 pi over T. So we can say that let's see, omega naught is greater than or equal to 2 pi over T minus omega naught. So if we look at the two frequencies of a reconstruction now, one option was a sinusoid with frequency omega naught, and the other option was another sinusoid with frequency 2 pi over t minus omega naught. And since we've shown that omega naught is greater, we want to pick the one with smaller frequency. So we get an aliased signal, cosine of 2 pi over t minus omega naught t minus v. So this is how aliasing occurs. And if t is less than pi over omega naught, in other words, we've sampled fast enough, then omega naught is greater, no, it's less than pi over t. So 2 omega naught is less than 2 pi over t. And we can say that omega naught is less than 2 pi over t minus omega naught. So here, notice that our original sinusoid, the simple option, has lower frequency. So we're just going to pick this, and we have a perfect reconstruction. So this might seem all theoretical at the moment. So let's put some numerical examples to all of this. So, and definitely recommend, if you want to get a full, more deep understanding with this, like to just play around with like samples in a Jupyter notebook. So we're going to start by just looking at a sinusoid, cosine of pi over 5t. Take it very simple, zero phase and a cosine wave. And let's suppose, so actually let's first look at the criterion. So omega max is equal to pi over 5. So the sampling theorem says we need our sampling rate to be less than pi over 5, which is 5. And now let's look at two cases. So let's suppose t is equal to 6. So if t is equal to 6, then our sampled signal, x of n, is going to be cosine of pi over 5 times nt, which is then equal to cosine, since t is equal to 6, it's going to be 6 pi over 5n. So since our sinusoid is 6 pi over 5n, then this reconstruction, a possible reconstruction, by letting n equal to t over capital T, is cosine of 6 pi over 5 times t over 6, which is just our original sinusoid, cosine of pi over 5t. So that's one possibility. And our other possibility is to then instead realize that cosine of 6 pi over 5n is equal to cosine of 2 pi n minus 6 pi over 5n, which is then, if we do the math, it's going to be, since 2 pi is equal to 10 over 5, it's going to be cosine of 4 pi over 5n. And you might notice here that 4 over 5 now has a lower frequency than 6 over 5. So another possible reconstruction is cosine of 4 pi over 5 times t over 6, which will then be equal to cosine of, let's see, 2 over 3, so then 2 pi over 15t. So another possibility. And since this one is lower frequency, we can conclude that sinc interpolation reconstructs cosine, let's write it here more clearly, yeah, cosine of 2 pi over 15t. And this was because we were like over this sampling theorem limit, which said that t needed to be strictly less than 5 for a perfect reconstruction. Because it was greater than or equal to 5, we had an imperfect reconstruction. 2 pi over 5 is obviously not equal to pi over 5. Now, another possibility, now let's suppose we're actually at the sampling criterion, t is less than 5. Let's suppose t is equal to 2. And now we can kind of see that if x of n is going to be cosine of pi over 5, and t, which is equal to cosine of 2 pi over 5n. And we want to compare this, maybe like we should have said like versus this one. Cosine of 2 pi minus 2 pi over 5n, 2 pi n minus 2 pi over 5n. And our other possibility would be 10 over 5 minus 2 pi over 5 would be, hold on a sec. Yeah, no, it should be 8 pi over 5 n. So immediately here we said this has a higher frequency. And 8 pi over 5, yep, which then gets reconstructed to cosine of 4 pi over 5t. And cosine of 2 pi over 5t would just get reconstructed to cosine of pi over 5t. So this one has lower frequency. So sync interpolation reconstructs cosine of pi over 5t and is perfect. All right, so last thing to kind of talk about is maybe let's go back to the discussion problem. The discussion problem itself, I pull it up, asks about now a sinusoid. The sinusoid is kind of unfortunate. We need to convert it to cosines, mainly just due to the conventions of how phasors work. So let's say we're given x of t is equal to sine of 0.2 pi t. And this is in fact equal to cosine of 0.2 pi t minus pi over 2. And now the way this works, we can again do the whole like same thing where we just kind of take two possibilities, but we're essentially asking what t creates an aliased copy f of t is equal to minus sine of pi over 15t. So we already know that like we're going to be in this quote unquote non-ideal case where we're looking at 2 pi over n minus the original frequency. So to actually put the math together, x of n, if we sampled it, is just going to be cosine of 0.2 pi nt minus pi over 2. And we want to now look at cosine of 2 pi n minus 0.2 pi nt plus pi over 2. And this is because, again, cosine of 2 pi n minus x is equal to cosine of x. So once we do that, we can factor out the n and see that cosine of 2 pi minus 0.2 pi t times n plus pi over 2 is going to be our, like, kind of, I guess we're just simplifying. And then if we reconstruct, we can reconstruct x of t equal to cosine of 2 pi minus 0.2 pi t times t over capital T plus pi over 2. which is then just equal to cosine of 2 pi minus 0.2 pi t. Sorry, it should be cosine of 2 pi over t minus 0.2 pi plus pi over 2. Now we can kind of ask, what t can we sample at to recover this other signal? You might notice that this is equal to cosine of pi over 15t plus pi over 2. So we just need to find a t such that the frequencies match. So such that might be easier, might be more clear if I write pi over 15 first. So pi over 15 is equal to 2 pi over capital T minus 0.2 t, 0.2 pi. And if we solve this, we're going to get 4 pi over 15 is equal to 2 pi over t. And this tells us that t is equal to 15 over 2, or 7.5. So hopefully now this is a little more clear than before. And if we had picked some smaller t, if we had picked some t that satisfy the Nyquist criterion, then we would have a perfect reconstruction. But because we're picking some larger t, we had an imperfect reconstruction. And we were able to find the t that gave us this imperfect reconstruction. All right, so that pretty much summarizes everything I had to say about this. If you have any questions, as always, feel free to ask on Piazza, office hours, or just feel free to reach out by email. All right, for the discussion. So I think the main takeaways are the fact that we sample by evaluating at evenly spaced intervals, and we reconstruct using sync interpolation by kind of picking the lowest frequency sinusoid that fits all the data points. And if we sample fast enough meaning like the sampling period t is less than pi over omega max, we can always guarantee a perfect reconstruction. If not, we're going to see some sort of aliasing. And like one example here is we just reconstruct some lower frequency sinusoid because we haven't sampled fast enough. So that's pretty much all for discussion today. Thanks for coming out. And as always, if you have any questions, feel free to stick around and ask.